Hello everyone, can you hear me? Uh, okay, I'm going to be learning calculus this stream. Yeah, so it has been quite some time since I last learned math. This was streamed 1 month ago. I've been learning C++, then circuit. I need to start this up, but I need some revision, so I'm going to be reading. I'm going to do a quick read and then do some questions. So I just opened this website. Click below to use the most recent version. I have the PDF version, so if this website is slow, I'll just switch to the PDF version. Is there a way to get rid of this? Okay, so vector valued functions, I'll try to do all of these 4 chapters. So yeah, I already did them before, but I wasn't really good with them. I'm still not good with them. Also, in this website, I wrote some proofs, whatever proofs I can find. Linear algebra, I think. Or is it in calculus? No, I think it's in calculus. It's here. Yeah, so if I want to get back to proofs, I'll just have to view these. Okay, so graphing, plane curve, space curve. Create a graph, okay. Limit and continuity, limit of a vector valued function. So here's a vector, and then here are 2 components. So the limit of this is the limit of each of the components. And similarly for the derivatives. Path it traces is called a plane curve. If it's 3 dimension, then we call it a space curve. Any representation of a plane curve or space curve using a vector valued function is called vector parameterization of the curve. Okay, let's see what do we have here. Give the component functions. Actually, let's open Desmos as well. Yeah, let's just Desmos. Give the component functions for the vector valued function. So, okay, so the first component is 3 secant t and the second component is 2 tangent t. So I need to go to the answers. It's in chapter 3, right? So it should be 3 point something. If it loads, that is. Given r, which is 3 sec t plus 2 tan t, find the following values if possible. So pi over 4, we just replace t with pi over 4, with these input values. Okay, evaluate. I'm only going to be doing the blue ones because I want to make sure that I got the answer right. Given the vector valued function r cos t and sin t, find, let's do 5a. Find copy. Hold on, there's an error. Because my tablet is not assigned to this monitor. It's assigned to my second monitor. I'll just fix that quickly. How do you change the monitor? Okay, now it works. So 5 RT is, I will write it like this, cos T in the I direction, and then sine T in the J direction. Find the following values. So this is pi over 3. So limit of this pi over 3. So limit of this pi over 3 is the limit. I'll just write it over here. So limit of this is the limit of this and the limit of this. Limit pi over 3. And hold on, cos pi over 3 is 0.5. So this, so cos pi over 3 would be 0.5 in the I direction. And then sine pi over 3 would be, how do I get this as a, okay, 0. Hold on, I have a calculator with me. Never mind, I will just write 0.87. 0.86. Well, let's just write 7 in the J direction. So which chapter is this? Exercise 2.7. Too far up. Yeah. Half and root 3 over 2. Let's see, what other questions should I do? Or should I do questions from the next chapter? Most of them seems to be about graphing. Consider the curve described by the vector valued function. This. What is the initial point of the path corresponding to R0? What do they mean by initial point? Initial point. Or are there multiple points going through R0? So let's take this, copy. This is question 33. R0. And K. So 50 e to the power of 0 is 1. This is 1. This is 1. 50i plus it with. So there's no j. 5 minus 5, right? And there's no k. And I feel like this answer is wrong. Let's just check. Yeah, 50, 0, 0. It was correct apparently. 0, j, 0, k. So I think like limits, it would be the same with derivatives and integrals. So if r is f plus g, then the derivative of r is derivative of f plus derivative of g. The same thing in the 3 dimensions. Here's the proof. Okay. Using the properties of derivatives of a vector valued function. So r and u, calculate each of the following derivatives using the properties of the derivative of vector valued function. So for dot product, we follow the multiplication rule. And it's even same for cross product. Derivative of the first times the second plus the first times the derivative of the second. Okay. Just need a reminder for that. So let's why is it so slow? Do example 3.6. This is the wrong picture. I don't know why it's so slow. Hold on. I'll just close some background application. See now it works. Example 3.6. So the derivative of these two would be, let's just find the derivative of this. So derivative of this would be derivative of each one. So 6t plus 8, the derivative would just be 6. And then 4t squared plus 2t minus 3, the derivative of this would be 4 times 2, 8. T plus 2, this j, then plus it with 5, just 5. Okay, and now for u, the derivative, I will write it like this. The derivative is 2t and then 2 and then 3t square minus 3. So derivative of the first times the second hold on, I'll write this the other way. So we have 6, just 6, 80 plus 2 and then 5. Sixty plus 8, 4t square plus 2. Never mind this. I'll just multiply it just like that. Or I can just bring the picture down. So this times this. You're multiplying each component, right? Wait, with multiplication of vectors, we multiply. No, we do cross product. Sorry. I don't think they have multiplied vector with vector before, have they? Because we haven't done matrices yet. So vector, no, they did dot product or cross product. Okay, where was I? Yeah, the calculus. Yeah, I was here. So derivative of this dot product. Okay, 6t plus 8. So with dot product, we just multiply them component wise, right? So 2t times 6t plus 8. Or no, sorry. It's 6 times t square minus 3. 6 times t square minus 3. So that's the first bit. Eight t plus 2 and then 2t plus 4. And then 5 t cubed minus 3t. And then this would be equal to 6t square 18. 8 times 2 is 16 t square. And then 32 t plus 4t, 4 times 2 8, and then 5t cubed minus 3t 36 plus 8. And now we need to do dot product of this and then RT. So that would be UT dot product, the derivative of RT, that is 6, 8, hold on. It should be derivative of this. Six t plus 8. And am I? No, it's 2t. Sorry. I'm copying. I think a lot of the times when I get the wrong answer is because I end up copying the wrong thing. 2 2 times 4t square plus 2t minus 3. 3t square minus 3 times 5t. 12t square, then 16t. 4 times 2 is 8t square plus 4t minus 6. 15t cubed minus it with 15t. And then, okay. So, the derivative of the dot product would be the sum of these two, right? So that's 12 plus 6, 18. plus 16t minus 18, and then this and this. So 24t square plus it with, okay, I'm getting confused. I'll just underline it. This is, yeah. So 16, 8, 36 and 4, 40t plus 2, and then these two, 15 and 5, so 20, and then 15, 15, 30. Minus 30t. If it's taking too long, then I guess I wouldn't bother. Then let's see. The answer is here. So for this, no, wait, we are supposed to, with dot products, we are supposed to add them, right? I keep forgetting. Hold on. Yeah, in the end, we are supposed to add them. Okay, okay. This is wrong. This, and I think I should start using different colors. Hold on. I think Alt C. Yeah, I should. Plus, and then 5t cubed minus 15t. Now if we add them, 16, 6, and then nothing else. So 22t square, and then 36t minus 15t, 21t, oh, and then I forgot the cube, and yeah, minus 18 and 8. Yes, this is the final answer. So what are all the squares? We have 12 and 8. So 20 t square. Uh, we have 16 minus 15. So 1 and then plus 4. So 5t. Right? Did this, and we did 16 minus 15 plus 4. Then we have plus 15 over there, and then minus 6 over here. Right. So now if we add both of these, what we get is, hold on, I'll just put this. And for t cubed, we have 20 t cubed. For t square, we have 42 t square. For just t, we have 26 t. And then minus 26. Let's see. 20, 42, 26 minus 16. I minus 15. Whoops. No, it's still minus 26. Where is the error? So I have minus 18 plus 8. Twenty, 42, 26, 20, 42, 26. Those are all correct. How did I end up with minus 26? It should be minus 16, so I have 10 extra. Okay, let's see. So 6 times 3, 4 times 2 is 8. Okay. Well, here 2 times 3 is minus 6. Where did I get minus 16 from? It's supposed to be minus 6. Then this will become, after minus 10, it will become minus 16. Now let's do this. Actually, let's just do the first one. So we have the derivative. And we have so how do I do this? Okay, I'm not able to remember how we did this. Was it like these two components like the multiplication of these two minus these two and then plus these two. Was it? Hold on, let me remember what cross product was. Cross product. Oh no, it was more complicated than that. So I think I will remember it easier with determinants. I, J, K. Six, six, 8t plus 2, 5, t square minus 3, 2t plus 4, t cubed minus 3t. 6, 8t plus 2, 5. Yeah, now let's remove all this. This is, so for the I part, this times this minus this times this. 8t plus 2, 8t plus 2 times it by t cubed minus 3t. This times this minus this times this minus 5. Yeah. And then for j, so we start with minus this times this minus this times this, but the sign is flipped. Minus this times this plus this times this. So this t square minus 3 times 5. Now minus 5 with 6 times it with this. And then for the k part, 6 times 2t plus 4 minus t square minus 3 8t plus 2. So let's see. 8t plus 4 minus t square. And then minus 6 minus actually plus 2t cubed minus 6t plus 2t cubed minus 6t. 5 times 2 is 10. And then 20 here. Six times 3 is t. 6 times 2 is 12. And then, so this 8t square. So, no wait, it's cubed. Plus it with 2t square, right? And then, yeah, 24 t cubed. What am I doing? You have t squared times both of these, so that's how we got 8t cubed plus 2t square, and then minus 24t minus 6. Wait, so it would be this, which is one part, plus it with the other cross product. Let's just simplify this. So we have 84 plus it with 2t cubed minus it with 24t square minus 16t minus 20. Eighteen t minus 15 minus 2t square. And then this is plus 24t. That goes with plus 12. And then this will become plus 6. Then over here, plus 30. And then now with the other one, you also need to calculate this cross product, this. And that is ijk 2t to 3t square minus 3. 2t to 3t square minus 3. And r is, hold on, What is R? Oh, I'm in the wrong chapter. Six t plus 8. 6t plus 8. 4t square plus 2t minus 3. 4t square plus 2t minus 3. So 2 times 5t, and then minus that with 3t square. And then we have j, but instead of, we start with the bottom. 6t plus 8. 6t plus 8 times it with 3t square minus 3. And then 2t times 5t. It's just 10t square. Is this correct? The derivative of u. Yeah. Now then we have 2t times 4t square plus 2t minus 3. Then subtract that with 2 times 6 is 12 t minus 16. Now let's see if we can simplify this. This is taking a really long time. 10t minus 3 times 4 is 12t square. And then this, and then I think I should put brackets just so I don't get confused. This, and then this, and then this. So minus 9t square. Then 12t square minus 6t plus 9. Six times 3 is 18t square. Hold on, no. 18t cubed. So this times this is 18t cubed. And then this times this is 18t. plus it with 8 times 3, 24 t square minus 24 minus 10 t square. Now we have this part. 2 times 4 is 8 t cubed plus it with 4t square minus 6t. Now for the first part, there's only one uh, like one term with degree of 4. Then for the degree of 3, also one term, so minus 6 t cubed. As for square, you have 9 and 12, so minus 21 t square. But because there's a minus here, it becomes plus. And then we have just for degree of 1, minus and minus comes plus, so plus 16t plus 9. 18t cubed minus 24 minus 18t plus 14t square. Eighteen t cubed minus, let's just do it, 14t square minus 18t minus 24. And then the last step is to add them, right? Component wise. Okay, let's just see what the final answer is. Okay, okay, there was a mistake here. They did not say R cross product U, they said U cross product U. Anyways, at least that was a practice. I hope I got it correct though. Vectors and space cross product. Okay, let's see what's that tangent question. Recall from the introduction to derivatives that the derivative at a point can be interpreted as the slope of the tangent line to the graph at that point. In the case of vector valued function, the derivative provides a tangent vector to the curve represented by the function. Consider the vector valued function r is equal to cos t plus sin t. The derivative of this function is minus sin t plus cos t. If we substitute the value of t pi over 6 into both functions, we get this. The graph is this. Okay, so the derivative at a point for any vector valued curve would be the tangent line, because that's by the definition of derivative. I'm using my right hand rule. So the first finger is the first term, the middle finger is the second term, and the thumb is the direction of the cross product. I need to remember that. And where do they do the determinant thingy? Yeah, this times this. Minus this times this. And then for j, normally it's from here to here, but because there's a minus sign, it would be flipped. It would be v1 times u3, then minus it with u1 minus v3. Okay. Let C be a curve defined by the vector valued function r and assume that the derivative of r exists when t is t naught. A tangent vector v at t naught. Okay, wait. So we have some vector valued function, and then at t naught we assume that the function is defined over here. We have r t defined by vectors I and, so this is I, this is j. Defined by I and j, we have rt. We're assuming it's defined at t naught. A tangent vector is any vector such that when the tail of the vector is placed at rt naught, so we have t naught and then the, how do I draw an arrow? Derivative will be, it touches one line. Thing like this is good enough. The derivative at t naught. Vector, so this vector is an example of a tangent vector at point t is equal to t naught. Furthermore, assume that the derivative of r is not 0. Okay, so what they mean by this is, oops, if it's a straight line, right, the graph continues and it's a straight line, then the derivative here is 0. So assume the derivative is not 0, so somewhere on a curve, the principal unit tangent vector at t is defined to be, okay, so it's basically this vector, but as a unit, as a, the length, as a length of 1. So the length is 1. This and this, the length is 1. That is a unit tangent vector. I don't know what they mean by principal. Finding a unit tangent vector for, let's do u. U t 3t square, 3t square plus 2t is the I part, t minus 4t cubed. That is the j part. Plus it with 6t plus 5. So the derivative is, at what point are we finding this? So the derivative is 6t plus 2 to minus 12t square 6. There's no 2 actually. And then the length of this vector, is you take the square of all of them. Whoops. This plus 2 square plus it with 6 square, which is 36. $36t, and then 6t times 2 is 12t, and then 12t again, so 24t plus 4, and then plus it with, okay, what was 12 square? 144 plus 36. So the unit tangent vector would be this divided by this, right? I can add 4 to 36 to get 40. Or is that correct? 4 to 36. 6 times 6. Why does it say 10? Hold on. So the first step is the derivative. The derivative, I'm guessing, is correct so far. And then the second step is this plus 40. So they took 2 out. Okay, so I was correct, but they took 2 out. They took 4 out, and then they square rooted the 4. That's why we have half. Instead of 6t plus 2, we have 3t plus 1. And instead of 12, we have 6t square. Okay, I get it. And then for the integral, we integrate each part, right? What's the next chapter? Arc length and curvature. Okay, I think let's go to the next chapter. I took a lot more. I think that question took a lot of time. I should have at least I got a practice with cross product because I really forgot that. So before I go into this chain arc length function and its derivative. So the arc length formula for a curve defined using parameter function x and y between b and a is this. So b is the larger one. So it's x derivative of x square plus the derivative of y and then square. So these two functions are defined by the parameter t. And this is how you find the arc length. Now let r be yti plus xtj, the arc length uh, traced by rt between b and a is, so we have these two. This is assuming rt defines a smooth curve. Is if rt is three-dimensional, then we have, it's like the Pythagoras theorem but for derivatives. But there is one thing I don't understand. Okay, never mind. Okay, never mind. Suppose a is a constant and b is a variable. We can define the arc length function as this. So sb, b is a variable. According to the fundamental theorem of calculus, the derivative of the arc length is the length of the derivative of r. Okay. Calculate the arc length for each of the following vector valued function. Okay, let's see. Should I clear this canvas? Yeah, I should clear it. So, what they want, calculate the arc length for each of the following vector valued functions. Let's try R T uh, T cos T. Actually, the derivative of RT would be derivative of the first times the second plus the first times the derivative of the second. Derivative of the first times the second plus the first times the derivative of the second. So this is correct. And then for the second one, derivative of the first times the second plus the first times the derivative of the second, and then it's just 2. Okay. We have this. Nope, this is wrong. We have all of this squared square plus all of this square plus this square, which is just 4, and then square root. So cos square this times this, and then this would happen twice, right? And then 2 over here, and then this plus this, and then where do we go from here? So we have this and this, which is just 1, and then we can add it here to make it 5, right? Plus 5. What else do we have? We have minus 2t sine t and then plus 2t sine t cos t. So these two cancel out. This and this cancel out. And then should this be just a single t? Nope, t square. So we are left with just t square plus 5, right? Find the arc length for. And okay, so we need to find between 0 and 2 pi. With respect to t, which is so this first it will be 0, 4 pi square plus 5. Is this correct? Okay, so this part is correct. And then hold on. No, I've done this wrong. t square plus 5 dt. How is the integral of this? Hold on. Is this something like memorized already before? I don't remember doing this. So t square plus 5. Wait. Derivative of t square plus 5 to the power of half. So derivative of this. So half t square plus 5 minus half. And then times this by 2t plus 5. Hold on. Maybe if we can try substitution. U is equal to plus 5. Du is equal to du over dt. 2t. Okay, I can't clear. I will have to reference it back again. Maybe I did do it, but I can't remember. Okay, anyways, I'll just check it later. Okay, what else do we have? Now we now have a formula for the arc length of a curve defined by a vector valued function. Let's take this one step further and examine what an arc length function is. If a vector valued function represents the position of a particle in space as a function of time, then the arc length function measures how far that particle travels as a function of time. The formula for the arc length function follows directly from the formula for arc length. Okay. So arc length from a fixed some point A, where the starting point T is A. A useful application of this theorem is to find an alternative parameterization of a given curve called an arc length parameterization. Recall that any vector valued function can be reparameterized via a change of variables. For example, if we have a function R is 3 cos t, 3 sin t, that parameterizes a circle of radius 3, we can change the parameter from t to 4t, obtaining a new parameterization 3 cos 4t, 3 sin 4t. The new parameterization still defines a circle of radius 3, but now we only need to use values from 0 to pi over 2 to traverse the circle once. Suppose that we find the arc-length function st and are able to solve this function for t as a function of s. We can then reparameterize the original function by substituting the expression for t back into rt. The vector valued function is now written in terms of parameter s. Since the variable s represents the arc length, we call this an arc length parameterization of the original function rt. One advantage of finding the arc length parameterization is that the distance traveled along the curve starting from s0 is now equal to the parameter s. The arc length parameterization also appears in the context of curvature, which we will examine later in this section. Okay, when is vector calculus? Aren't we already doing vector calculus? I guess there's more to it. Find the arc length parameterization of each of the following curves. Okay, so we copy this. So the arc length parameterization is just the integral. So what we need to find SB is integral B A R and then D T. 3.10a. Should I say example? Yeah. So the derivative of RT is cos becomes minus sine t y should be plus. And what else? The length is this square, so 16 sine square t plus 16 cos square t, and then since they will both add up to 1, we'll be left with just 16. So we are left with 4. Now the arc length is it's from 0, right? From 0, just 4. No, wait. B. T dt. So the integral is for t b 0, which is for b. And then, yeah, that's the arc length. Find the arc length parameterization for each of the following curves. So we found the arc length. So wait, if we input t here, we get 4t, which means t is this, and then what? Yeah, so instead of rt, we can do r like this. For cos ti. I plus, is it plus or minus? Plus 4 sine. Why did they write s instead of s over 4? Why did they do this? Since the original restriction on t was given by t is more than 0, the restriction on s becomes s by 4, which is more than equal to 0, or s, which is more than equal to 0. Hold on, I don't understand. Shouldn't this be s by 4? Guess if someone in the comments can let me know. Okay, let's just read through this one. T plus 3, 2t minus 4, and then 2t. So first they're finding the length. So we have 1, 2, 2. Hold on, how is it 1, 2, 2? So it's starting from 3. Why is it 1, 2, 2? Where did the variable t go? So t plus 3 square, 2t minus 4 square, and then 2t square. Okay, they end up with this. Substituting this over here, they get this. The thing is, I still don't understand why. Why, why don't they write s over 3 plus 3 instead? Instead, they just write s. I feel like if we don't define 4, if we just write r with the input of s, do we get the same curve? No, we don't get the same curve. Or we get the same curve, but wouldn't it be like stretched or shrinked with respect to the input variable? Let C be a smooth curve in the plane or in space given by R, where S is the arc length parameter. The curvature K at S is given by this. So we have, okay, I removed we have this and this. If we have this tangent, suppose this is unit length, unit tangent vector. So this, I need a steeper curve. So we have, let's say, this over here. So we should make this a unit vector. So the derivative of this with respect to the arc length. So the change in the tangent, the length remains the same. So we are only checking the direction. So the change in this with respect to the arc length gives the curvature. So the greater curvature, the greater this thing changes. Like the length will remain the same. If you do a very tiny increase, it will go up in that direction, right? Like this unit tangent vector. Like if it's over here, if you increase it just a little bit slightly, the vector would change direction. So if it changes direction a lot, that means the curvature is great. If it barely changes, that means the curvature is small. So we can define curvature like this. If C is a smooth curve defined by given by R, then the curvature K of C at T is given by this. So derivative of the unit tangent vector divided by the derivative of R. If C is three-dimensional curve, the curvature can be given by this formula. Okay. if C is the graph of the function y is equal to f of x, then both the derivative of y and the double derivative of y exist. So the curvature of k at point xy is given by this. I think I've written the proof here. Let's see, curvature. Yeah, for flatter. I downloaded it. So the distance between would be very tiny. For flatter surfaces, there would be barely any change. For greater change, the unit vector will change a lot. So the derivative of t, there should be with respect to s, not t. So the derivative of the unit tangent vector with respect to s is this chain rule. And then since the derivative of the arc length is the length of the derivative of r, we can write it like this. Then we could put r the other side. And substituting that into the original function, we get this. So the derivative of t divided by the derivative of r, and then only the length of both. This is the first formula. This is the second formula. Since the principal unit vector is defined like this, derivative of r divided by derivative of the length. Wait, hold on. Is this correct? Okay, there are several mistakes here. This should be derivative of r divided by derivative of the length of the derivative of r. Then we can rearrange it like this. And since the length is defined by derivative of s, we can define r like this. And then we can differentiate it again to get all this. We take the cross product. Wait. Okay, this ends up with a, and this is how we end up with the third formula. And of course, the last one is given as well. Find the curvature for each of the following curves at the given point. Copy. So let's see, we have 3.11a. So let's just do the first one. RT 4 cos t plus 4 sin t plus 3t. Find the curvature for each of the following curves at the given point. So curvature K is, I should write like, I think it's capital K. It can't curvature be, okay, actually never mind. T S. And what's the other formula? T and R. I think that's the easier one. I think this is also wrong. This is not like this. It's T as a function of the arc length. And then if you want the function of in terms of T, we use this one. So T we have T and we have R. For I keep forgetting the derivative sign. So 4 this becomes minus, and then sine t becomes cos t, plus it with, instead of 3t it's just 3 and not plus, like that. And the derivative wait, I did this last time, right? This square plus this square plus this square. Sine square plus cos square is 1, so we are just left with 16 plus 9. So we are left with 5. And as for t, so for t, the tangent vector, but we already have the derivative, right? So t is, we take the derivative this is the tangent vector. So now let's do the derivative of this. It has to be like that. The derivative would be this square plus this square plus this square. And since sine square and cos square is 1, we are just left with 4 square over 5 square. And plus that with 3 square over 5 square, which is 9 over 25. Oh wait, it's a tangent vector. Why? I don't know why. Wait, hold on. If the, wouldn't the length of this always be 1? So shouldn't this be 1 over r? derivative of r? No, that's the, hold on. The length of this would be 1. Hold on, no. Think I got it wrong. Cos t, and then this becomes minus sine t, and then this becomes a 0. Cos sine, and now we do the length thing. (16/25) plus it with plus 0, but that doesn't matter. 32/25. Can we simplify root 32? Yeah. 4/5 root 2. So then this divided by so we have this divided by this. That's just 4 root 2, right? But it doesn't feel right. Hold on, let me just see the answer. Four over 25. Okay, let's see. No, wait. This divided by this. And also I made a mistake here. This is 16. No, I did not make a mistake here actually. Root 2 divided by 5. 4 over 25 root 2. Okay, I understand the 5, but where's the root 2 here? How did they get just 4 over 5? So 4 times 4 is 16. 5 times 5 is 25. 16 over 25 plus it with 16 over 25. Hold on. Yeah, I think the mistake is here maybe. Because I don't see. The root 2 is missing. Yeah, I think the mistake is here. Okay, the normal and binormal vectors. We have seen that the derivative of r of a vector valued function is a tangent vector to the curve defined by r, and the unit vector t can be calculated by dividing uh, the derivative of r by its magnitude. When studying motion in 3 dimension, two other vectors are useful in describing motion of a particle along a path in space: the principal unit vector and the binormal vector. Hold on. Okay. So the normal vector is derivative of t divided by the arc length. So it's a unit vector. The binormal vector at t is defined by their cross product. So wait a minute. Okay, so from what I remember, if we let's say t of t is a continuous function. Let's say this is continuous. Continuous. I don't know that's how you spell it. And length is always 1. Is equal to 1. So if you have, like, it's defined like this at a certain point with the tail at 0 and t of t here. If we put the tail at 0, let's say the vector looks like this. If we keep the tail at 0, as t will be changing, the vector will be going like around a circle. Like the t is changing and then it's going around a circle. Maybe it's increasing, but it will always be in a circle. So the path it traces is a circle. So it's like this, and then it's like going around as t changes. Maybe it increases and then decreases and increases again. So what that, since the path it traces is a circle, because the length is always 1, that means its derivative would look like, would be at the tail over here. Its derivative would be perpendicular to t. So let's say t is going here, then its derivative would be facing that direction. And yeah, it would be perpendicular to t. If it's going in that direction, then the derivative would be going in that direction. And also it will be perpendicular to t because it's like tangent to circle. And if it's a unit, so the normal vector is a unit tangent vector, and it's perpendicular to t. So n, t, and b are three vectors that are perpendicular to each other. Where is it? Yeah, I think this picture is wrong because it doesn't follow the right hand rule. If I put t in my index finger and n in my middle finger, b is like going downwards, not upwards. That by definition, the binomial vector is orthogonal to both the unit vector and the normal vector. Okay. The unit and binomial vector form a plane that is perpendicular to the curve at any point on the curve, called the normal plane. So t and n, if you make a plane out of t and n, that plane is tangent to the curve at this point. Three vectors form a frame of reference in the three-dimensional space called the Fernet frame of reference. The plane is determined by the vectors t and n form the osculating plane of C at any point P on the curve. Okay, t and n, if you make a plane from t and n at point P, then it's called an osculating plane. I mean, okay, I want to end stream soon, but I also want to do the next chapter. So I'll just read this and then I'll go to the next chapter. Suppose we form a circle in the osculating plane of C. Okay, so like over here, osculating plane is like the plane of T and N. Assume that the circle has the same curvature as the curve does at point P and let the circle have radius r, then the curvature of the circle is given by 1 over r. We call this r the radius of the curvature. Yeah, I think I proved this. Yeah, the radius. If we choose this point, it's called an osculating circle. The equation of a circle is, okay, so what I prove over here is that for the oscillating circle, the radius is defined like this. And basically this is like 1 over k. It's like 1 over the curvature. So k is 1 over r. We call r the radius of curvature of the curve and it is equal to the reciprocal of the curvature. If the circle lies on the concave side of the curve and is tangent to the curve at point P, then this circle is called the osculating circle of C at P as shown in the following figure. Okay, let's just, now this time it's a new chapter. Our starting point is using vector valued functions to represent the position of an object as a function of time. All of the following material can be applied either to curves in the plane or to space curves. For example, when we look at the orbit of the planets, the curves defining these orbits all lie in a plane because they're elliptical. However, a particle traveling along a helix moves on a curve in 3 dimensions. Let R be a twice differentiable vector valued function of the parameter t that represents the position of object as a function of time. The velocity vector v of the object is given by this. So R is represents the position and then v is the derivative of R. The acceleration vector a is defined to be this, so double derivative of R. The speed is defined to be, it is the velocity, it's just the magnitude and not the direction. So S over T what is S over here? Because in physics I remember S being displacement, but I don't think, maybe distance. Since R can be either in can be in either 2 or 3 dimensions, each vector valued function can have either 2 or 3 components. In 2 dimensions we define R like this and in 3 dimension like this. Then the velocity, acceleration, speed can be written as shown in the following table. Studying motion along a parabola. A particle moves in a parabolic path defined by the vector valued function r is t square, with t square in one direction and 5 minus t square in the other direction, where t measures time in second. Find the velocity, acceleration, and speed as a function of time. So RT five minus t square. Derivative of r would be 2t like that, and then the derivative of the inside. Now what? That is the velocity, and the acceleration is the double derivative. Two, hold on. Now the derivative of the first. Okay, this is going to take time. Is there a simpler way? No, never mind. Uh, Hold on. Let me calculate this separately. Wait, minus 2 and this half would cancel out, right? We just left with minus 1. So you have low T high minus high. This becomes D low upon bottom squared. This is all of this is the acceleration. But what about speed? Speed is like the first derivative. It's like this, right? Four t square plus it with square of this t square and square of this. This is the speed. Okay, let's see. So okay, what about this one? The first derivative is correct. The second derivative, the acceleration of derivative of velocity. So 2 minus 5, 5 minus t square minus 3 over 2. How did they get the minus 5 out? Wait. So the derivative, we have low, d high, minus high, d low, upon bottom squared. How did 5 come out though? Shouldn't this be t? Yeah, I will have to check this later how this is, how they got this. So, okay, for this one, 2t becomes 4t square. 2t becomes 4t square, and this becomes t square over 5 minus 2t. Right. To gain a better understanding of velocity and acceleration vectors, imagine you are driving along a curvy road. If you do not turn the steering wheel, it would continue in a straight line and run off the road. The speed at which you are traveling when you run off the road, coupled with the direction, gives you a vector representing your velocity as illustrated in the following figure. However, the fact that you must turn the steering wheel to stay on the road indicates that your velocity is always changing, even if your speed is not, because your direction is constantly changing to keep you on the road as you turn to the right. Your acceleration vector also points to the right. Okay, components of the acceleration vector. We can combine some concepts discussed in the arc length and curvature with the acceleration vector to gain a deeper understanding of how this vector relates to motion in the plane and in space. Recall that the unit tangent vector t and the unit normal vector n form an oscillating plane at any point P on the curve defined by a vector valued function r. The following theorem shows that the acceleration vector A lies in the oscillating plane and can be written as a linear combination of the unit tangent and unit normal vector. The acceleration vector A of an object moving along the curve traced out by a twice differentiated function r lies in the plane formed by the unit tangent t and the principal unit normal vector n to c. Furthermore, A is the derivative of the velocity. Wait, isn't a just the derivative of the velocity? Why is it so? V is the speed of the object and k is the curvature of c traced out by r. Okay, hold on. That's not velocity, that's speed. Tangential and normal components of acceleration. Let r be a vector valued function that denotes the position of an object as a function of time. Then a is like the double derivative of r. Then a, which is the double derivative of r, is the acceleration vector. The tangential and normal components of acceleration at and an are given by the formulas. So at is a cross product with t, and then an is a cross product with n. These components are related to by the formula. Okay. Here t is a unit tangent vector of the curve defined by r, and n is the unit normal vector. The normal component of acceleration is called the centripetal component of the acceleration. So centripetal would be like the one going outside, and t would be one going along the path. To understand centripetal acceleration, suppose you are traveling in a car on a circular track at a constant speed. Then, as we saw earlier, the acceleration vector points towards the center of the track at all times. As a rider in the car, you feel a pull towards the outside of the track because you are constantly turning. This sensation acts in the opposite direction of the centripetal acceleration. The same holds true for the non-circular path. The reason is that your body tends to travel in a straight line and resists the force resulting from the acceleration that push it towards the side. Note that at point P, the acceleration vector is pointing backwards. This is because the car is decelerating as it goes into the curve. Find components of acceleration. A particle moves in a path defined by the vector valued function. This at measures time in seconds and distance measured in feet. Find at and an. Okay. So let's see what we have. R is t square 2t minus 3. 3t square minus 3t. And then the first derivative is like this. You have 2, and then we have 6t minus 3. And then we have the second derivative. 2, 0, and then 6. Let's see if this is correct. Now the acceleration, A cross product with t. So this over here is v t a t So t is, wait, when we say tangent, we mean tangent of r, right? So yeah, so this divided by this. Let's see. And 4t squared plus 4 60 minus 3 squared. Okay, yeah. This times this. Wait, hold on, no. 60 times 60. 36 t squared. Minus it with, then 6 times 3, 18. But that should happen twice. Hold on. Then it's 36 again. Then 3 times 3, 9. Is this correct? This is not. This is like this. Do we need it at a specific point? No, it's just general. And then 13. And then the tangent vector would be all of this divided by this. And then the acceleration would be a dot v. Hold on. So if we do a t dot t, we are actually doing dot vt like that. And a dot v, we multiply them component by component, right? 4t 36 t minus 18. Is this okay? Just for the t component, is it correct? For t minus 18. Wait, the dot product. Oh yeah, we multiply each component and then we add them, right? I forgot. Hold on. Plus. So we are left with 40 t minus 18. Forty t squared plus minus 3060 plus 13. And we have to do a similar, no, not similar. For the normal vector, it's a dot n, and I don't understand why is it like this. Why is it like this though? A dot n, which is v cross product with a divided by the vector v. Okay. I mean, I don't wanna. I'm gonna take a lot of time. I'll just read through this. So from this, they got this. Which is the acceleration, magnitude of the acceleration square, minus it with 80. And then they ended up with 14 over 40 t square minus 36 t plus 13. Now let's look at an application of vector functions. In particular, let's consider the effect of gravity on the motion of an object as it travels through the air. Now, how it determines the resulting trajectory of that object. In the following, we ignore the effect of air resistance. This situation with an object moving with an initial velocity but no forces acting on it other than gravity is known as projectile motion. It describes the motion of object from golf balls to baseballs. First, we need to choose a coordinate system. If we are standing at the origin of this coordinate system, then we choose the positive y-axis to be up, the negative y-axis to be down, the positive x-axis to be forward. Okay, the effect of gravity is in a downward direction. So Newton's second law tells us that the force on the object resulting from gravity is equal to the mass of the object times the acceleration resulting resulting from to gravity, or should it be resulting from gravity? Or Fg is equal to mg, where F represents the force from gravity and g represents the acceleration resulting from gravity at Earth's surface. So initial position, acceleration, and final position. Newton's second law tells us that F is equal to ma, where a represents the acceleration vector of the object. This force must be equal to the force of gravity at all times. So we therefore know that this is this and A is Gj. Isn't G like already in the direction of J? No, G is a scalar value, right? And then J gives the direction. Now we use the fact that acceleration vector is the first derivative of the velocity vector. Therefore, we can rewrite the last equation in the form like this. By taking the antiderivative of each side, we obtain gtj plus ci for some constant vector ci. To determine the value of this vector, we can use the velocity of the object at a fixed time, say at t0. We call this initial velocity. Therefore, v0 is g0j. So that means c1 is v0. This gives this. Next, we use the fact that velocity is the derivative of the position. This gives the equation. The derivative of the position is equal to minus gt plus initial velocity. Taking the antiderivative of both sides of this equation leads to this. S is minus gt plus initial velocity. You're taking the antiderivative of the entire thing. Then we are left with this. Now we have another unknown constant vector c2, and we will use s0 to determine that. So s0, and then we are left with c2 is equal to s0. So st is minus gt square plus initial velocity plus initial speed, initial position. S is the position, right? Let's take a closer look at the initial velocity and the initial position. In particular, suppose the object is thrown upward from the origin at an angle theta to the horizontal with initial speed v0. How can we modify the previous result to reflect the scenario? First, we can assume it is thrown from the origin. If not, then we can move the origin to the point from where it is thrown. Therefore, S0 is 0 as shown in the following figure. Okay, so S0 is 0. During an Independence Day celebration, a cannonball is fired from a cannon on a cliff toward the water. The cannon is aimed at an angle of 30 degrees above the horizontal. And the initial speed of the cannonball is 600 feet per second. The cliff is 100 feet above the water. Find the maximum height of the cannonball. So we have 3.16. V0 is 600 feet per second. But we are only considering the vertical part, right? So, like, 600 here. We have 30 degrees above the horizontal. So yeah, we need the opposite part. 600 it is 300. And cos would be wait, hold on, I want to check something. Times it by cos 30. Okay, yeah. 600 cos 30 is equal to 519.62, which is this speed over here. So V initial velocity up. So VU is like when initial velocity up only the up direction, which is 300 feet per second. Now, if we use this as 300, positive 300, and let's do now. Let's say the final velocity is 0 feet per second. So that is when it reaches its maximum height. So the initial position is 0. Let's assume initial position is 0. But we don't know the time though. What we do know is that G is minus 9.81. Wait, it's not minus 9.81. That's meters per second square. What is G like in feet? Hold on, let me check this online. Gravitational force in feet per second. 32.2 feet per second squared. 32.2 feet per second square. Right, so we have that. So what do we have? We have V final is equal to minus G dj. I think let's use G as a vector. G is a positive vector going up, which is 32.2 feet per second square. Why did they use G as a positive? Now I have to put the negative outside. Plus it with V initial, which is the upward V we calculated here. So 0 T and then this is a velocity, right? No, what am I? No, it should be minus 300. This is in the J direction. This is J. This is J. This is J. Well, uh, but we don't need this J. Minus 300 divided by minus 32.2. This is 332.2. 9.316. Let's say 9.32 seconds. And then I can plug in initial velocity and then 9.32 over here. Sorry, I mean over here. 9.32 initial velocity and then initial distance is 0. Okay, let me just minus half. G is 32.2. 32.2 and then T square. Plus it with initial velocity, which is 300. Nine 9.32. Let's see, minus half. 1,397. Is that correct? 1,397. Well, it is in feet, right? It says 1,406. I think the 9.32, there might be minor differences. They collected as 9.375. Yeah, I think they use 32 feet instead of 32.2. Yeah, now I'm getting this. I think I will just end this. Wait, how much is left? Okay, I will just read about the Kepler's law and then I will end the stream. During the early 1600s, Johannes Kepler was able to use amazingly accurate data from his mentor Tycho Brahe to formulate his three laws of planetary motion, now known as Kepler's laws of planetary motion. These laws also apply to other objects in the solar system in order to in orbit around the sun, such as comets and asteroids. Variations of these laws to satellites in orbit Variation of these laws apply to satellites in orbit around Earth. So the three laws are: the path of any planet about the sun is elliptical in shape, with the center of the sun located at one focus of the ellipse. A line drawn from the center of the sun to the center of the planet sweeps out sweeps out equal areas in equal time interval. Okay, so if this and this were like 2 months apart, this and this were 2 months apart, the area these two make is equal. The ratio of the squares of the periods of any two planets is equal to the ratio of the cube of the length of their semi-major orbital axis. The ratio of the square of the periods of any two planets is equal to the ratio of the cubes of the length of the semi-major orbital axis. Kepler's third law is especially useful when using appropriate units. In particular, one astronomical unit is defined to be the average distance from Earth to the Sun and is now recognized to be this much, or approximately 93 million miles. 93 million miles. We therefore write 1 AU is 93 million miles. Since the time it takes Earth to orbit the Sun is 1 year, we use Earth years for units of time. Then, substituting 1 year for the period of Earth and 1 AU for the average distance to the Sun, Kepler's third law can be written like this. For any planet in the solar system, where T p is the period of that planet measured in Earth years, and dp is the average distance from the planet to the Sun measured in astronomical units. Therefore, if we know the average distance from a planet to the Sun, we can then calculate the length of its year. Okay. Uh, all right. I think this is something I would read off stream. Okay, I will end the stream here then because I don't feel like doing any more exercises. And yeah, next stream, like I need to fix some things on my website and I need to start making notes on this. And then next stream, I will start studying whatever the next chapter is. Seems to be differentiation with several variables. Yeah, I will end the stream here then. Okay. See you guys next